Hello everyone and welcome to yet another session of NPTEL course in Herbal Product Technology and Regulatory Science. In the previous session, we saw a set of novel drug delivery systems applied to herbal formulation, and that was liposomes. We saw traditional herbal formulations and the advantages that the novel drug delivery systems have to offer in terms of its safety, compatibility as well as bioavailability of these drugs. In this session, we are going to study yet another novel drug delivery system which is applied to formulating herbal preparations, and that is referred to as phytosomes or sometimes synonymously called as herbosomes. So what exactly are phytosomes or herbosomes? Let's learn about them. So when we said liposomes, we said that liposomes are something which are lipophilic bodies. So if we can allays it to phytosomes, these are bodies which contain phytochemicals, or these are carriers of phytochemicals is how we can define them. Now in terms of its appearance, they appear very much similar to your liposomes. That means they are made up of phospholipid bilayer. So this phospholipid bilayer makes them vesicles and not micelles. So they are concentric vesicles, basically microscopic bilayered vesicles about same size as that of your liposomes, ranging somewhere between 30 nanometers to several microns, with their instability increasing when the particle size gets over to about 800 to 1000 micrometers, leading to multilamellar structures. Now, if you see in terms of vesicles, again you can have a single concentric vesicle, or they might be a multitude of such vesicles, up to hundreds of such vesicles which are responsible for that. Then you might ask, what is the difference? There is a very little difference between this, and that difference is they often contain, when you were talking about liposomes, you saw that this in between layer which hosted your water or the aqueous region contain most predominantly the water soluble drugs, whereas your fatty acid chains contain your lipophilic drugs. Here you will not find your drugs herein, but you will find somewhere associated at this layer. So this contains bioactive plant compounds, especially phytochemicals which are associated with the phospholipids, especially phosphatidylcholine, to create a very lipid compatible and cell membrane like structures. We call them as vesicles. Now this phytochemicals which associate with these heads especially need to have a active hydrogen which is involved, and hence there is a specificity. When we said liposomes, we said anything that can dissolve in water, hydrophilic drugs, anything that can dissolve in lipids, lipophilic drugs can be incorporated. But when it comes to phytosomes, we have a limitation that these are particularly phytochemicals and the association is very molecular. That means it's not the whole extract that is going to be associated. They are going to be very selective phytochemicals which are going to be associated with the phospholipids, and for those phytochemicals it is mandatory to have active hydrogen, and this can be in form of a carboxylic acid group like a COOH group, a hydroxyl group, an amine primary or secondary, or maybe something like a polyphenol which can integrate to the phytosomal structure. So let's just see clarity into a subtle difference between these two. Now first, coming to similarities between these two, in terms of similarity, both of them have identical shape, both of them have identical size, both of them are made up of phospholipid bilayer. So the similarity in shape, size, lamellar structure, phospholipid bilayer, both of them may exhibit what are called as SUV, small unilamellar vesicle, large unilamellar vesicle, or multilamellar vesicle arrangement, and so on. So these are all the similarities. So what is the difference? Now when it comes to difference, let's understand when you take about drugs, or when you are thinking about drugs, take for example water soluble drugs. Now when we are talking about liposomes, quickly brushing up with the previous concept, this particular region hosted most of your aqueous layer, and this aqueous layer contain your water soluble drugs. Now when it comes to the phospholipid bilayer, you remember this region was the one which has the acyl chain or the lipophilic chain of the phospholipid, and as a result this hosted what are called as your lipophilic drugs. So in terms of its ability to host drug, a liposome can host aqueous or water soluble drugs in its core, that is the cavity, whereas it can host the lipophilic drug basically into the long tails, that is your aliphatic tails of the phospholipid. Now when it comes to phytosomes, the appearance is very much similar, but what happens is when we talk about phospholipids, this phospholipid forms hydrogen bond associations, and for forming hydrogen bond associations we require functionalities like, if you recollect, COOH, you might require a hydroxy, or you might require something like an amine group. A primary as well as secondary amine does the work. So in order to form this hydrogen bonds, the hydrogen bonds form exclusively at the polar head. So you will find if this is a drug, the drug is not hosted inside the vesicles, but the drug is chemically bound. So here it is physical entrapment, whereas in this case the drug is chemically bound. And as a result, in terms of its appearance, you will see most of the phospholipid bilayers hosting your drug by what is called as a stoichiometric association. So here you can load based on the solubility. Here you can load based on the stoichiometry. Generally 1:1 or 1:2, or in some cases 2:1, but the ratios may change, and specifically whatever drug is actually binding to the polar head, it is mandatory for it to have this functionality, whereas in liposome there is no such mandate of a active hydrogen group. Now when you are preparing liposomes, again we saw that in the places of liposomes where you want to form association, or when you want to prepare liposome, you could easily mix organic solvent, aqueous solvent, everything was involved. But when you are talking about hydrogen bonds here, if you use water or any other polar solvents, the hydrogen bonds with the drug moieties, especially the hydrogen bonds with the phytochemicals, would be lost. So in that case it is very important that during preparation we use exclusively aprotic solvents, so that these bonds are remain intact and the hydrogen bonds are not displaced. So generally this happens in presence of aprotic solvents. Whereas in this case it is very non-specific, you can use both water based, buffer as well as lipophilic solvents. So liposomes host both drugs In this case, phytosome host drugs which have active hydrogen. Liposomes can even host lipophilic drug. This is not always the case here, depending upon the functionality. Here the drug may be just physically entrapped, and as a result, if the if the liposome breaks open or is ruptured, all your drug will release. In this case, because the phytosome binds to the drug, even if there is rupture or opening, your drug will still be associated with the phospholipid, and as a result, the chances of leakage and draining of liposomes and release of the drug doesn't happen here. So that's the difference between these two, and as a result, now because your drug is bound to the phytosomal, especially the polar head of your phospholipid, in that case the bioavailability increases. In this case, the cell is taking up the phospholipid, but what is happening is the drug is released in the environment. Here, when the cell takes the phospholipid, the cell also drags in the drug along, and as a result, the bioavailability here is much enhanced. As compared to your phytosomes. Now let's move on to the components of phytosomes. The components of phytosomes are very much similar to that of liposomes, which includes the main component phospholipids. Now phospholipids are the components which render a very nice inertness as well as biocompatibility to your phytosomes. So this might involve again your natural phospholipids. This include your glycerophospholipids as well as sphingomyelins like your soy lecithin, sunflower lecithin, egg lecithin, or in some cases purified compounds such as phosphatidylcholine, phosphatidylserine, phosphatidylethanolamine and so on. But in majority of the cases, phosphatidylcholine is much preferred. Nowadays you get even synthetic phosphatidyl derivatives such as dialkyl as well as trialkyl lipids such as your dipalmitoyl phosphatidylcholine derivatives. Now in addition to that, very similar to that of your liposomes, you also require membrane stabilizing agents, and these are often your sterols. For this reason, again you can take your cholesterol, which can be in the ratio 1:2 or 2:1 depending upon the stability of the membrane that you are looking for. But yes, nowadays even other steroidal derivatives such as beta sitosterol are involved to enhance the membrane permeability, fluidity as well as the stability. Now liposomes often involve surfactants, but when it comes to phytosomes, the surfactants are very rarely or minimally used. In case you don't get the optimal size, especially in a desired nanometer range, when you want a very tiny phytosomes, in that cases surfactants may be involved to stabilize and further process your phytosomes to prepare a smaller, what are called as SUV, smaller unilamellar vesicles. But later on, this surfactants can be removed by help of certain membranes like your dialysis membrane. Now generally while preparing your phytosomes, non-ionic surfactants, especially the spans and twins like your span 60, span 80 or twin 60 or twin 80 are preferred. Now process of preparation, this again differs with respect to liposomes. So when it comes to preparation of phytosomes, the first thing that you are going to do is you are going to prepare an extract. Now while preparing extract, one thing we remember is here you don't load the whole extract, here you load only the phytochemicals, like specifically the phytochemicals possessing a COOH group and hydroxy group, amine group are going to bind. The remaining phytochemicals will just remain in the aqueous phase, they will not form any association, and as a result you have to be careful. Now once you are preparing the extract, we do not load an aqueous extract here. We don't want water, because water is going to form hydrogen bond and that will not allow the phospholipid to associate with my phytochemicals. Here we generally prefer aprotic solvents, and as a result, while extraction, if you have used water, it has to be completely dehydrated or removed. You require a very solid extract which is then dispersed in an aprotic solvent, which can include something like a chloroform, dichloromethane, dimethyl formamide and so on. So take aprotic solvent, disperse this extracts. Some compounds might be soluble in it, some compounds might not be soluble. So for the compounds that are not soluble in it, it makes sense to filter them or centrifuge it off. So once the dispersion and a good solution of this is prepared, post the dispersion, you take this and then you add your phospholipids to it. Now this phospholipids, you allow it to stir. Generally the ratio of plant extract is to phospholipids, that is that you dispersed in your DCM or any aprotic solvent is to the phospholipid. It generally 1:1 or 1:2, but in again specific cases it might be changed. Take the extracts, disperse it in aprotic solvent, add your phospholipids and reflux it for some time. During the refluxation, this phospholipids form hydrogen associations with the phytoconstituents. Now once for several hours with an elevated temperature, like the elevated temperature need not shoot up, otherwise that will deteriorate your phytosome. So just keep it like 50 to 60 degrees Celsius, which will help to keep that good bond. So keep it refluxing so that the solvent is kind of reconstituted, that remains and the association is complete. Now once your reaction has happened, the hydrogen bomb associations have happened, that is the time you remove the solvent. Now removal of solvent can be done either by solvent evaporation, just evaporate it using high vacuum, or in some cases you can add an anti-solvent which is again going to cause precipitation, but this anti-solvent should again be aprotic. So use something like a hexane mostly to precipitate the phytosomes out of DMF or any other solvent. In some cases freeze drying is done, wherein the preparation, especially the phytosome, is brought to a very cold temperature like -80 degrees Celsius, and then from there on the solvent is gradually removed. This results in an ultra fine amorphous powder, and this amorphous powder can then be reconstituted whenever you want to consume it. Another option is you take the solvent and then do a spray drying process. During the spray drying process also the solvent evaporates, resulting into a drug polymer, that is a drug phospholipid being precipitated in form of fine powder. You just need to kind of rehydrate it whenever you want to consume it. So yes, that is especially drying is very important here, because the moment you put it in water, again the associations change. So you need to be little careful while creating those kind of associations, and generally it is easily reconstituted by rehydration whenever you want to use it. So preparation of phytosomes as compared to your liposomes does not involve use of water or any other protic solvent, for the reason if the protic solvent is used, your phytochemicals will not form hydro association, that is hydrogen bonds, with the phospholipids. So this is again a difference between your liposomes and phytosomes as far as preparation of both of them is concerned. So once the phytosomes are prepared, again you can size reduce it, that is decrease the particle size in order to get more stable small unilamellar vesicles of uniform size and distribution. So generally you can use what are called as probe sonicators, which are nothing like a rods. So that is dipped into a solution containing phytosome inside a water bath, so that the frequency goes or travels through the water bath much easily, and the frequency is kept really high, like 43 kilohertz to about 480 kilohertz. Now as you go towards higher frequency, there is lot of in situ heat generation, and that might lead to deterioration, but if you work at higher frequency, there is a greater chance of getting small unilamellar vesicles. So higher the frequency, finer the vesicles you will get. Higher the frequency, definitely there is a chance of deterioration. So you need to tread carefully in this area, but if you are able to dissipate heat and control the temperature, you can get very good quality SUVs, that is small unilamellar vesicles here. Another one is a press, that is typically a French press, what is called as extrusion method. In this again you need to put your phytosomes by the same press which is used for liposomes as well, and here again a high pressure is applied. When high pressure is applied, it is then extruded through a pore. Now this pore size is defined by your membrane filters. So you have membrane filters of different particle size. In some cases it might be as fine as 0.2 micron or so on. So depending upon what is the particle size of the membrane, you might get a uniform unilamellar vesicles of those size. Again you can use high pressure homogenization with a very high pressure ranging somewhere between 500 to 1500 bars, that is 50 to about 150 megapascals, and you to do it for like 3 to 10 times through the same machine. So though that is called as passes. So after about 3 to 10 passes, you will get a ultra fine or very small vesicles. Also optionally, if you have large vesicles like your large multilamellar vesicles, you can break them into small pieces or smaller vesicles by continuously freezing and thawing it. So when you do it at few hour intervals, the vesicles break up and eventually give rise to a smaller particle size. Now once you prepared it, the quality control of the phytosomes are almost similar to that of your liposomes. So you can do what is called as particle size analysis, which is very vital because that determines the stability, that also determines the shape and the attributes. Now this can be done by dynamic light scattering. So dynamic light scattering, like we discussed, so if it is a big particle, when light falls on it, it goes very smoothly. So if I am having multiple waves, my DLS graph goes very smooth. But as opposed to it, when you have finer particles with huge Brownian motion going by, so say for example tiny particles moving, and this is going to be up and down. So your DLS scattering is going to be more random. The more the scattering you will get, more is less is the particle size. Apart from that, you can also carry what is called as electronic microscopic techniques, wherein you can have scanning electron microscopy, which kind of sees the particles from the surface. So it analyzes it. In this case, if you want to see the internal structure of it, they do what is called as freeze fracture. So you freeze it and then crack it open. When you crack it open, you call it as freeze fracture, and that cracked version of it might expose the inside vesicles. The more better, easier option is what we call it as the transmission electron microscopy, and in this case what will happen is it's like a slice, again frozen via cryo-TEM or sliced, and what happens is electron passes through this and through vesicles. Through vesicles it is more restrained, through lamella it is even more restrained, and in the aqueous layer it can pass easily. So it creates an image of it, and that is how you can do it. Similarly, you can use a very charged tip which moves very close to your particle, and that is what we call it as atomic force microscopy, wherein the probe goes very close to the particle, analyzes it and gives the image of it. Similarly, you can analyze a zeta potential, which is directly correlating to the stability of your phytosomes. So the zeta potential should be on a negative side, especially that's preferred for phytosomes. So somewhere between higher than minus 20 to minus 50, or somewhere at a very negative side when you go it, you prefer it. But as it comes close to 0, the chances are your particles carry no charge, so they'll coalesce to each other. So you need to be careful that you have a good zeta potential value, good surface charge. So this can be measured again by dynamic light scattering, because of the Brownian motion is associated with the charge. Electrophoretic mobility, that is how much, when you put in an electrode, your particles migrate toward electrode. More the charge, faster will be their rate of migration. Lower the charge, very slowly they will migrate. So that gives you the charge. Even you can do photon correlation spectroscopy, where you can correlate again in terms of lamellarity, how much lamellae are present. You can do an NMR. Basically you have phospholipids. So this phospholipid head, if it is tagged with a radio labeled phospholipid, I come to know location wise where it is, and if I do a good imaging with NMR, I exactly know what is the adjacent lipid or adjacent molecule to it, and that image pattern of my P31 NMR gives me a good idea about the lamellarity. Not only that, I can see the stability, temperature stability, as well as phase behavior when I subject it to something called as a differential scanning colorimetry, which measures the behavior of your polymer, especially your phytosomes, over a range of temperature. So wherein your temperature is gradually increased, and if there is any melting or any transition, that is what is called as exothermic or endothermic process, heat is either released or absorbed. So during this, that is your differential scanning colorimetry, the heat absorbed or released is also captured. In a similar manner, we do what is called as thermogravimetric analysis, where you see a weight change with respect to temperature. Even that gives us a very good idea about the phase behavior. Now the last part, but most important part, is how much drug was my phytosome able to encapsulate. I can do that by predominantly first centrifuging it, especially do an ultra centrifugation, because the particle size is really fine here. So when you do ultra centrifugation followed by dialysis, you generally get the drug or lamellar rupture. The lamellas are ruptured to release the drug, and the drug release is injected into a machine such as HPLC or GC in order to analyze the content. Or you can even do a simple UV if your method is UV sensitive, or by using certain derivatizing reagents. So in terms of its applications, numerous phytosomes have been formulated in market for varied applications. Here are few examples. If you see a silibin which is obtained from your milk thistle, when you see a silibin, what happens here is it's a hepatoprotective and an antioxidant. And if you see your phospholipids, phospholipids have a good protective effect on liver. They go and reside in the liver and can also help specific delivery of the silibin inside the liver. So they can help. Not only are phytosomes used for oral application, they also use nowadays for skin care and as well as in cosmeceuticals. So here for oral application, the general dose loading was about 120 mg. Again, if you see second examples, they are about ginkgo. Ginkgo is used as an anti-aging. It prevents neurodegeneration and it protects your brain and vascular lining. So ginkgo phytosomes or ginkgo phytosomes containing ginkgo flavonoids, which are the active compounds in it, almost 20% flavonoids, or that is 24% flavonoid loading was done with help of phytosomes. Now again, olive oil, they contain numerous antioxidant principles, polyphenols, especially the flavonoids, and free sterols as well as tocopherols. All of them form association with the phospholipids, and that phospholipids can provide, once they are bound to that phospholipids, they can provide antioxidant, anti-inflammatory as well as anti-hyperlipidemic activity. Again, coming to grape seed, they are very high in antioxidant, especially the proanthocyanidins. This proanthocyanidins from vitis, especially your grapes, are acting as a nutraceutical as well as a systemic antioxidant. So, a good dose loading up to 50 to 100 mg was done. Your havthones containing your flavonoids for cardioprotective and hypertensive, centella containing your bacosides for your vein, skin as well as brain disorders, as well as echinacea containing your echinacea, which is a immunomodulator as well as a mood elevator, has also been used and formulated as your phytochemicals. Now let's compare the advantages and limitations herein. So advantages and limitations of your phytosomes, if you see here, are in terms of advantages, you will see that liposomes are definitely more bioavailable as compared to your phytosomes. The reason being, when they are phytosomes, they are associated by chemical bonds, and when they are associated by chemical bonds, they can be absorbed easily along with the phospholipids. So that enhances its bioavailability as well as stability. They don't really leak in when the liposomes open, and as a result the dose required is very less. Now when the dose required is very less, definitely the toxicity associated with it also decreases. Not only that, the phospholipids are biodegradable, they have good hepatoprotective effect. Now coming to limitations, again if I have to compare here with liposomes, the spectrum of drug loading, the amount of candidates which I can load here as a drug is limited, because I said I need to have COH group, hydroxy group or even amine group, which was not in the case with liposomes. So here they fall little bit back because this liposomes are non-specific, whereas phytosomes are more specific. Again, the production costs are quite high. The polymers, especially phosphatidyl or phospholipids, are very expensive, and they also don't have a good temperature stability. So you can't really cross temperatures like 100 degrees Celsius when you are thinking of phytosomes or a stable preparation. And yes, over a period of time they lead to little aggregation and leakage, and that's the reason the shelf life of this preparation is little shorter. And definitely because of this processing, the association, scaling up still is an issue, but yes, it is commercialized and such preparations containing phytosomes are available in market. So here are a few references that you can look forward to if you wish to know more about the phytosomes. And thank you everyone for your patient listening. Thank you.